Madam, good afternoon, madam. Sir, shall I start the meeting? Sir, Muralidharan sir and Mandal sir.
Okay.
Yeah. Sure.
Thank you, sir. Thank you. Very good afternoon to everybody. Today we are gathered here for witness of the public Viva examination to Mr. Kumaraguru for the topic of metal oxide anode for electrochemical energy storage in rechargeable lithium-ion batteries application. I welcome head of the department and professors from the various institutions and also my dear colleagues and also the researcher for today's program. Today we have Professor Dr. K. Muralidharan, School of Chemistry, University of Hyderabad as our external examiner. So I would like to say a few words about the examiner. He awarded Ph.D. from IIT Kanpur and he moved postdoctoral fellow to the University of Idaho, USA, also postdoc research associate in Texas, USA. Then he joined Arabindo Pharma Limited, Hyderabad, and he moved IASC centenary postdoctoral fellow under supervision of Professor S. Ramakrishnan. And he joined assistant professor, University of Hyderabad, on the year of 2013. He published nearly 60 research articles with a very good impact factor, and the citation score is nearly 1100. Also, he guided 6 research scholars, and presently he guiding 7 research students, and also many postdoctoral fellow they are doing under his guidance. So I welcome Professor Dr. K. Muralidharan sir to this scientific forum. Welcome, sir.
Thank you.
Thank you, sir. And also I thank to accepting for my request as a thesis evaluation, sir. Thank you very much. And I am very much happy to welcoming Professor Dr. Dipankar Mandal, scientist, Institution of Nanoscience and Technology, Mohali, for our external examiner for this scientific forum. I would like to say a few words about Dipankar Mandal, sir. He awarded PhD from the Germany, and he have the experience as a scientist assistant Germany and a postdoctoral research from South Korea. Okay. So postdoctoral researcher from South Korea and also the assistant professor in Jodhpur University. And he is a total citation for Google Scholar 4,633, and he published 105 research article, and also he published 2 patents. I welcome sir, Professor Mandal sir, scientist, and also I thank for accepting my request for the Viva examiner. I'm very much happy, sir. Thank you, sir. I'm welcome, sir. Now, yes. Regarding the scholar, he completed MSc Chemistry, Madurai Kamarajar University, and he worked project assistant CSCR Sigri Karaikudi, and he joined JRF in DST SERP funded project at SRM IST, and also he awarded CSCR SRF total number of publication 25 and the citation of the publication 515. So, and also he attended more than 30 workshops as well as the national international conferences. So with this introduction, I hand over the session to the examiner for conducting the public Viva examination and declare the result. Sir? Sir, I'm audible? Yes, sir. I hand over the session to you, sir.
Okay, how to be conducted? We just, I invite Mr. Kumaraguru to make the presentation. After that, we'll interact with the candidate, and then I think our Dr. Deepak and Mandar also will agree for this one. So we'll conduct the same.
Guru, please, video mode.
Yes, sir. Yes, sir. Yes, sir. Thank you so much, sir. I am S. Kumaraguru. I am pursuing my doctoral research under the guidance of Dr. E. Sundaravadivel, sir, Department of Chemistry. Today, I am going to discuss about metal oxide anode materials for electrochemical energy storage in rechargeable lithium-ion batteries application. These are my academic activities. I joined in SRM-IST on December 2017, and I submitted my thesis on November 2021.
Actually, your slide not moved.
I think there is some.
Otherwise, you come out from the full screen, then you can move. Yeah, now it's moving.
Yes, thank you, sir. Overview of the presentation. This presentation consists of 5 chapters. Chapter 1 discuss about introduction, about batteries, lithium-ion batteries, and its advantages, disadvantages, principles of lithium-ion batteries, components. How chapter 2 discuss about experimental methodology, characterization techniques, fabrication of electrodes, slurry preparation, coin cell assembly, and electrochemical characterization techniques. Chapter 3 and 4 discuss about working chapters containing nickel oxide, cobalt oxide, manganese oxide composite, and tin oxide for energy storage application. Chapter 5 discuss about conclusion and important findings from the chapter 3 and 4 and the scope of future work. Chapter 1 introduction. Battery is a device which converts chemical energy into electric energy by means of electrochemical relaxation occurring at the double layer interface. It consists of 4 important components: anode, cathode, electrolyte, separator. Anode is a negatively charged electrode where the reduction reaction occurs, which gives electrons to the external circuit. And the cathode is a positively charged electrode which undergo oxidizing reaction and which accepts electron from the external circuit. Electrolyte is a medium for both the electrodes to conduct the ions. Separator is made up of polymers, and it is only permeable to the ions, and it is electrically insulating to prevent the short circuit of both the electrodes. Lithium-ion batteries introduction in 1981. Important invention of lithium cobalt oxide, commercial lithium cobalt oxide cathode materials invented by Goodenough. And in 1987, carbon lithium cobalt oxide fuel cell was assembled. In 1991, Sony commercialized the first lithium-ion batteries. Figure shows the energy densities of various batteries. In this, lithium-ion batteries received much attention due to its lighter weight, longer runtime, smaller NCs, and higher current. Other batteries have several disadvantages. Lead-acid batteries has large weight, and it is maintenance is very difficult. It exhibits low energy density. In case of nickel cadmium battery, cadmium exhibits toxic to the human beings as well as environment. Nickel metal hydride and lithium metal batteries are exhibit safety issues. Various configuration of batteries. Commercially available batteries are 4 types available: cylindrical, prismatic, coin cells, and pouch cells. Principles of lithium-ion batteries. Lithium-ion batteries consist of 2 electrodes, anodes and cathodes. In commercial lithium-ion batteries, anode is current collector is copper, on which graphite electrode material is coated. Similarly, cathode material is cathode current collector is aluminum, on which lithium cobalt oxide cathode material was coated. Lithium cobalt oxide has theoretical capacity of 140 milliampere hour per gram, while graphite has 372 milliampere hour per gram. And a commercial electrolyte is 1 ml LiPF6 dissolved in 1:1 ratio of EC-DEC mixture, and it was both electrodes were separated by a polymer separator. During discharge reaction, electrons move from anode to cathode. Correspondingly, lithium-ion moves. During the charge, electron move from cathode to anode, and corresponding lithium movement happening. Graphite has able to accommodate 6 moles of lithium. Cathode materials. Based on the structure, cathode materials are divided into majorly 3 types: layered materials, spinel materials, olivine materials. Layered materials, for example, lithium manganese oxide, lithium cobalt oxide, lithium nickel oxide. Spinel materials are lithium iron manganese oxide, lithium nickel cobalt oxide, lithium nickel iron oxides. Olivine materials are phosphate based materials: lithium iron phosphate, lithium cobalt phosphate, lithium iron nickel phosphates. Based on the energy capacity of the various cathode materials shown in figure. At a higher capacity was observed for the silicon-based cathode material, and the phosphate-based materials exhibits as a higher capacity as well as high voltage withstanding capacity. Anode materials, based on the mechanism, 3 types of anode materials were observed. Carboxylous materials, for example, graphite, lithium titrates, which undergo intercalation and deintercalation mechanism. Allying type materials undergo allying type reaction mechanism. For example, silicon, tin, germanium, antimony metals. Conversion type materials are cobalt oxide, nickel oxide, mostly transition metal oxide. Based on the capacity profile, various anode materials are shown in figure. In this, alloy type materials exhibits 2000 to 4000 milliampere hour per kg, but alloy type materials exhibits too much volume expansion, so that it has drawback. Similarly, tin and Si based anodes have also volume expansion problem. 3D transition metal oxides exhibits 600 to 1100 milliampere hour per kg and also high voltage capacity. Lithium-ion batteries issues and challenges. A lot of issues inside the while working of lithium-ion batteries. SEL decomposition, copper dissolution, lithium dendrite formation, lithium plating issues, current collector corrosion, structural disordering, like that. Advantages of lithium-ion batteries: high energy density, lightweight, long life, low self discharge, fast charging, maintenance low cost. Disadvantages: expensive thermal runaway, performance degrades at a high temperature, safety issues, requires protection sensors. Metal oxide anode materials. In 2000, JM Tascon Group first invented the transition metal oxide based anode materials for lithium-ion batteries. It has a theoretical capacity of 700 milliampere hour per gram, and it delivers 2 to 3 times higher than the commercial graphite, and also it is eco-friendly, environmental benignity, corrosion resistant, decent, economic. Mixed transition metal oxide, including stannates, ferrites, cobaltates, nickel refers to ternary metal oxides with 2 different metal triads rather than mixture of 2 binary metal oxides. Generally, mixed transition metal oxide can alloy with more lithium ions compared to mixed and normal metal oxides, owing to the complex chemical composition and resulting high reversible capacities. Mixed transition metal oxides are often more environmental benign than the transition metal oxide, particularly for cobalt oxides. This is schematic illustration of the conversion type mechanism happening in cobalt oxide. Figure A shows the before cobalt oxide before lithium. B is the initial stage of lithium ionization, and C is the formation of CO-rich LiO cluster, and D is the formation of interconnected COO clusters embedded in the lithium oxide nanocrystals. E is the formation of smaller cobalt oxide crystals, and F is the formation of COO nanoparticles. Objective of the work: the synthesis plan to synthesize nano-architected metal oxide materials for prepared via various techniques, and it is characterized with XRD, SEMTEM, EDS, FTA, TGA, XPS, etc. The electrified interface properties of electrodes were analyzed by electrochemical resistance such as CV, impedance, and galvanostatic charge studies, rate capability studies, to achieve the better electrochemical behavior of fabricated metal oxide materials for energy storage application. Chapter 2 discuss about experimental methodology and characterization techniques. All the chemicals, materials, solvents you purchased as analytically and used in the experimental studies without any further purification. The characterization techniques: the prepared materials were confirmed by the Bruker D8 advanced and panatical air switched up X-ray diffractometer. The stretching and vibration frequencies present in the of the materials were investigated with CMOS, IR tester, and the infrared spectrometer. The thermal stability of the material was inspected with the Nestec STER 2500 Regulus gravimeter. The elemental composition and the element present in the material was scrutinized with Oxford Institute Energy Dispersive X-ray spectrometer. The morphology of the material investigated with the FEI Quanta FEG 200 field emission microscope, GeoGem 2100 plus high resolution transparent electron microscope. The surface area of the material is estimated using quantagram Artoso IQ instruments bed nitrogen absorption isotome. The elemental state of the material was enumerated using thermoscientific multilab 2000 X-ray photoelectron diffractometer. The electrochemical studies was executed with biologic BSP 300 electrochemical station, Vonatech WPCS 3000, and newer battery cycle. Fabrication of electrodes, slurry preparation. Slurry was prepared by mixing active materials, super P carbon PVDF in the ratio of 70-20 and 10% with an appropriate amount of NMP, and coated on the copper foil with thickness of 9 micron, and it was dried at 120 degrees Celsius for 12 hours. After that, it is punched into disc via electrode cutter. The coin cell component consists of top can, spring disc, anode, cascade, separator, cathode, and bottom can. Electrochemical parameters: lithium file act as counter electrode, and punched electrodes were act as working electrode. Electrolyte is the 1:1 ratio of ECDMC. ECDMC contains 1 ml LiPF6. Separator is Selgard 2531, coin type CR2032. The coin cells were fabricated inside the Telex Lab 2000 glow box with less 0.1 ppm of oxygen and water, and it was crimped using hydraulic crimper. The fabricated coin cells were tested with newer battery cycle and monotech battery cycle. Electrochemical condition: the cyclic voltammeter was executed within the potential window of 10 millivolt to 3 volt at the scan rate of 0.1 millivolt per second, and we studied up to 5 cycles. Impulse spectroscopy was executed in the frequency range of 1 MHz to 10 MHz with the signal amplitude perturbation of 10 millivolt. Charge discharge study was executed at the current density of 100 milliampere per gram, except rate capability studies. Chapter 3: enhanced electrochemical behavior of robust nickel oxide, cobalt oxide, manganese cobalt oxide composite as an efficient and suitable anode material for lithium-ion batteries. This work got published in Ionics. Synthesis of NCM composite particles: nickel chloride 0.4 mole, cobalt chloride 0.4 mole, manganese nitrate 0.2 mole were dissolved in 60 ml of water. To this, sodium dioxide dissolved in 20 ml of water was added dropwise manner until pH 10. It is stirred for 3 hours. It shows green precipitate. After that, it was transferred to Teflon lined autoclave, and it was treated at hydrothermally treated at 180 Celsius for 24 hours. After allowed to cool to room temperature, it was filtered and repeatedly washed with water, and finally with ethanol. We obtained gray powder, and it was dried at 80 Celsius for overnight. After that, it was taken in a ceramic pot and placed in the tubular furnace and calcined at 400, 500, 600 degrees Celsius for various timings. We obtained the black powder labeled as NCM. The prepared material was confirmed by the X-ray diffraction studies. All the prepared materials exhibits spinel structure, and its planes were indexed to nickel oxide, cobalt oxide, and manganese cobalt oxide. The material prepared at 400 degrees Celsius exhibits manganese cobalt oxide as the dominant phase, while the material prepared at 600 degrees Celsius reveals nickel oxide as the dominant phase, and it is confirmed by the its JCBD card number. Morphological studies: material prepared at 400 degrees Celsius 2 hours, 400 degrees Celsius 3 hours reveals all the samples reveals microcubes, but these 2 samples reveals microcubes morphology with aggregated structure with the particle size of 150 to 200 nanometer, while the material prepared at 400 degree 4 hour and 500 degree 4 hours reveals 450 to 500 nanometer, and the corresponding ED spectrum is shown in EFG sets. It shows the presence of nickel, cobalt, manganese, and oxygen, and nickel, cobalt, manganese, oxygen were atomic percent were consistent with the experimentally taken mole ratio. Further, the morphology was confirmed by the HRTM analysis. From the HRTM analysis, we found that the particles were dense, and its facets were flat, and it has edged edges. And this figure this shows the despacing lattice fringes of NCM. It shows 4 lattice fringes. 2 lattice fringes has a despacing value of 0.47 nanometer, corresponds to triple one plane, and another 2 despacing values. Lattice fringes shows despacing value of 0.29 nanometer, corresponds to 220 planes of manganese cobalt oxide. The selected area electron diffraction pattern is indexed to 5 ring pattern, and it corresponds to 111, 400, 440, 444, 642 plates. The particle diameter was estimated using histogram analysis. The histogram analysis shows that average particle diameter of 188.22 nanometer with the total particle of 76. The elemental oxidation state was confirmed by the XPS analysis. Figure A shows the Na2P 4-level spectra of Na2P, and it shows its peaks were deconvoluted to 4 peaks, and the spin orbit doublet exhibits Na2P 3/2 and Na2P half corresponds to the Na in +2 oxidation, and the binding energy difference confirms this also +2 oxidation, and its satellite peaks confirms that it is in oxide form. 4-level spectra, 4-level CO2P XP spectra of CO2P shows deconvoluted to 8 peaks. It shows 2 plus 3 plus oxidation state of cobalt, and the binding energy difference is between two spin orbit doublets CO2p3/2 and CO2p half is between 2 electron volt corresponds to the it is in oxide form. Similarly, M1,2p high resolution vector deconvolute to 4 peaks, and it also shows 2 plus 3 plus oxidation, and it is in oxide form. O1 spectra shows 3 peaks, and the main broad peak noted at around 529 electron volt corresponds to the metal oxygen bond, while medium peak around 531 electron volt corresponds to the chemistry oxygen, and the low peak are greater than 532 electron volt corresponds to the oxygen ion low polarization state. The bed surface area measured by the NCM material exhibits 61.55 meters square per gram, and it exhibits type 2 isotherm with multi-layer of adsorption, and exhibits lower degree of porosity. Pore distribution analysis shows that it shows various pore sizes ranging from 2 to 16 nanometer, and it exhibits multiple pore sizes. Its range is confirmed that it is mesoporous. Electrochemical studies to analyze preliminary information about the NC material cyclic photometry was executed in between the 10 millivolt to 3 volt, and at the scan rate of 0.1 millivolt per second. During the cathodic scan, we observed 3 reduction peaks at 1.07 volt, 0.73 volt, 0.56 volts corresponds to the crystal structure destruction of NCM, SE layer formation, and reduction of metal oxide to metallic state. During the anode scan, we observed 2 peaks, 1.57 volt and 2.14 volt corresponds to the oxidation of metal to metallic oxide form, and 2.14 volt indicates mixed valence of manganese and cobalt. Figure B shows the real-time application of NCM material charge discharge studies. In the first cycle, it delivers 1271 milliampere hour per gram, and the flat plateau region around 0.9 volt corresponds to the SE layer formation. Then in the first cycle, we observed a higher capacity, which is due to the excess of lithium ions act by the force of the NCM material. In the first chart, we observed 930 milliampere hour per gram. In the second cycle discharge, we observed 903 milliampere hour per gram. The capacity loss between the first cycle and the second cycle is around 26.7%. And the corresponding cyclic profile is shown in figure C. From the second cycle onwards, the capacity keep on adding up to 126 cycles. This corresponds to irreversible disintegration of the NCM material and volume change. After that, the capacity keep on increasing up to 200 cycles and achieved 696 milliampere per gram at the end of 200th cycle. The initial Coulombic efficiency of the material was 71%. From it keep on increasing after the fourth cycle, it attains a stable state and achieved 99% of the Coulombic efficiency. Figure A shows the cycling performance of the material prepared at 400 degree 2 hour, 3 hour, and 500 degree 4 hour. All the it was studied at 100 applied current density of 100 milliampere per gram, and we observed less than 300 milliampere hour per gram even after 150 cycles. Figure B shows the cycling performance of the 600 degree prepared samples at various timings. We studied at 100 milliampere per gram applied current density, and we studied greater than 100 cycles. We observed greater than 450 milliampere hour per gram, which is greater than the commercially available graphite material. To understand the stability behavior as well as rate capability behavior of the material, we studied the different C rate studies. C rate study when the current density increases from 100, 200, and 300, 400, 500 milliampere per gram every launch cycles. The capacity keep on adding. When the current density returns to the original value of 100 milliampere per gram, it delivers only 254 milliampere hour per gram even after the end of 66th cycle. To understand the interface behavior of the prepared electrode, impedance study was executed. The impedance was recorded for the first cell as well as after cycling. The impedance was recorded. The semicircle starts around near to the origin, corresponds to the solution distance. The semicircle ends and intercepts at the x-axis corresponds to the charge transfer resistance. The inclined line at a low frequency region corresponds to the diffusion region. After cycling, the semicircle was low. It indicates that charge resistance was low, which indicates that it has compared to fresh cell. After cycling, conductivity increases, and the inclined line was small, which says that SEL formation arrests the lithium-ion diffusion across the interface, and it is fitted with the equivalent circuit. The circuit is shown in figure. RS is the solution resistance. R1, R2, R3 are the SELA resistance, binder current conductive battery resistance. R3 is the charge transfer resistance. Q1, Q2, Q3 are the corresponding oxygen base elements. W is the Warburg diffusion. Table 1 compare the effect of preparation condition on the electrochemical energy storage properties of the prepared NCM materials. In this material prepared at 600 degrees Celsius, 2 hours, 4 hours, 6 hours, samples exhibit greater than 450 milliampere hour per gram. And also the material loading for the each electrode is approximately 2 mg, and we obtained the yield nearly greater than 1.5 grams in 8 ml of hydrothermal synthesis. Able to compare the obtained result with the previously reported literatures. Conclusion: we have successfully prepared the NCM composite material via hydrothermal method. The synthesis material oriented in its final phase. The prepared material at various annealing temperatures were characterized with HSM and temp, which shows that microcubes morphology with approximate size of 200 nanometer to 300 nanometer with the edge edges. In the first cycle, it delivers a discharge capacity of 1270 milliampere hour per gram at the applied current density of 100 milliampere per gram. At the end of 200th cycle, it delivers 696 milliampere per gram with the Coulombic efficiency of 19%. Chapter 4 discusses about resilience scale synthesis of tin and nanosphere as electron materials for lithium and energy storage application. This work published in INX. 0.4 experimental synthesis of tin and nanospheres. 0.06 mole of tin sulfate dissolved in 200 ml of water. In another beaker, terephthalic acid 0.4 mole, sodium dioxide 0.8 mole dissolved in another 200 ml of water. Terephthalic acid was added dropwise to the tin sulfate solution, and it is stirred for 5 hours and it is filtered and repeatedly washed with water and finally with ethanol. After that, it was dried at oven at 80 degrees Celsius for overnight, and it was taken in a ceramic boat and it was placed in the tubular furnace at 450 degrees Celsius for 6 hours and 650 degrees Celsius for 6 hours. We obtained tin oxides. The prepared material confirmed by the X-ray effects studies. The crystalline grains noted the crystalline grains observed 110, 101, 200, 111, 220, 211, 220, 002, 310.
Kumaraguru, can
Sir?
you go back to a previous slide?
Yes, sir.
Okay. Okay, go ahead. I'll talk to you later.
This place corresponds to tin oxide, and the material prepared at 650 degrees Celsius reveals highly crystalline, while compared to 450 degrees Celsius. The crystalline size was calculated using the divisor formula D equal to K lambda by beta cos theta. D is the crystalline size, K is the shape vector, lambda is the wavelength of X-ray is used, beta is the full width of maximum in radians, lambda is the beta cos theta, theta is the angle of diffraction. The NCM tin oxide prepared at 450 degrees Celsius reveals 26.33, and tin oxide prepared at 650 degrees Celsius reveals 18.91 nanometer. The material prepared at 650 degrees Celsius reveals small crystalline size. Further, the searching frequencies of the bonds in the tin oxide was confirmed by the FTI study. And we recorded for the terephthalic acid, tin oxide, terephthalic acid, and tin oxide. The stretching and vibration frequencies observed at 1672, 1010, 1416, 1281, 926, 878, 725 per centimeter corresponds to the carbonyl asymmetric and symmetric stretching of C double bond C, C single bond O, OH bending, CH bending, and out of plane ring bending vibrations of the terephthalic acid. In addition to that, in tin oxide terephthalic acid composite, in addition to that, we observed 605 per centimeter square peak was observed. It corresponds to the tin OH bond formation. In tin oxide, slight shift in the stretching frequency noted and observed at 596 corresponds to the SNO bond formation. Morphological studies. The prepared tin oxide terephthalic acid composite exhibits fluffy flake-like morphology with aggregated structures. Its size is ranging from 7 to 10 micrometer. Its facet were flat and it has B and C shows the morphology of the tin oxide. The tin oxide exhibits nanosphere-like morphology with aggregated structure. Corresponding ED spectra shown in D, E, F. D shows the presence of tin, oxygen, and carbon. E and F shows the presence of tin and oxygen. The tin and oxygen were present in the 1:3 ratio. atomic ratio. Further, the morphology was confirmed by the HRTM analysis. From the HRTM analysis, we found that the party size was ranging from 20 to 30 nanometer. Selected area diffraction was noted, and it is into the d-spacing value observed are 3.10 angstrom, 2.45, 1.64 angstrom corresponds to the 110, 101, 211 planes. Bed surface area was recorded and it exhibits bed surface area of 20.23 meters square per gram. This type 2 isotherm with the H3 hysteresis loops. Pore distribution analysis shows that a single pore size of 8.84 nanometer. It exhibits mesoporous structure. Thermal stability of the material was recorded from room temperature to 800 degrees Celsius at the ramp rate of 10 degrees Celsius per minute in the nitrogen atmosphere. Bad ethylene acid exhibits two weight losses. The initial weight loss was correspond to the decomposition of the carboxyl group in between the temperature 230 to 300 degrees Celsius. The second major weight loss noted at greater than 300 degrees Celsius corresponds to the decomposition of the framework moiety. And tin oxide prepared at 450 degrees Celsius reveals small weight loss greater than 400 degrees Celsius corresponds to the incomplete removal of the terephthalic acid. The material prepared at 650 degrees Celsius reveals almost no weight loss. It indicates that complete removal of terephthalic acid. Figure BCD shows the X-ray XPS photoelectron spectroscopy of tin oxide. B is the overall surface spectrum. C shows the core level SN3D spectra. It is deconvoluted to two peaks. The peak binding energy values observed at 485.8 and 494.2 correspond to the spin orbit doublet 3D SN3D 5/2 and SN3D 3/2. The binding energy difference is 8.43 electron volts. It indicates that tin in presence in oxide form as well as it can say 4 plus oxidation state. O1s core level XP spectra of O1s shows that it's single peaks and it is deconvoluted to two peaks. The major peak observed at 599.6 electron volt corresponds to tin SNO bond formation, and a small peak noted at a higher binding energy value of 530.6 corresponds to the chemistry observed oxygen. Electrochemical studies. The CV was performed 10 millivolt within the potential of 10 millivolt to 2 volt at the scan rate 0.0 millivolts per second. During the cathode scan, three peaks noted at 1.04 volt, 0.76 and 0.15 volt corresponds to the tin oxide to tin formation reduction. 0.76 corresponds to SELA formation. 0.15 corresponds to tin lithium alloy formation. During the anode scan, two peaks noted at 0.53 and 1.25 volt corresponds to the decomposition of the lithium tin alloy as well as lithium oxide formation. 1.25 volt corresponds to the SNO formation. Charge discharge studies was of tin oxide prepared tin oxide electrode studied up to 50 cycles at the current rate of 100 milliampere per gram. In the first cycle, it delivers 1149 milliampere per gram. During the first charge, it delivers 720 milliampere hour per gram. In the second discharge, it delivers 703 milliampere hour per gram. Even after 20 cycles, it exhibits greater than commercially available graphite electrode, delivers high capacity than the commercially available graphite electrode. Corresponding cyclic profile is shown in figure C, and we studied up to 50 cycles. At the end of 50 cycle, it delivers 54 milliampere hour per gram. It exhibits initial first cycle Coulombic efficiency of 61%. From the second cycle, it achieves nearly 92%. From the fourth cycle onwards, it maintained at the level of 95%. Different C rate studies was executed to understand the rate capability behavior of the tin oxide electrode. We ramping the current density from 100 milliampere, 200 milliampere, 400 and 600 milliampere per gram. The capacity discharge capacity keep on adding. When the current density returns to the original value of 100 milliampere per gram, it delivers 47 milliampere per gram. At the end of 50 cycle, it achieves 47 milliampere per gram. At the 41st cycle, it delivers 172 milliampere hour per gram. To understand the interface resistance as well as interface behavior, impedance was executed for first cycle as well as after cycle cell. The impedance after cycling exhibits semicircle was low. It indicates that enhanced conductivity was noted in the from the second cycle onwards, as well as diffusion layer is small. It indicated that lithium diffusion across interface was restricted by the SELA formation, and it is fitted with the equivalent circuit. RS is the solution resistance, RSE is the SELA resistance, RCT is the charge transfer resistance, QC, SEI, and QCT are the corresponds to the constant phase element. QW is the Warburg impedance. Conclusion. In summary, tin oxide nanospace was successfully synthesized via co-precipitation method. Tin oxide oxide and tin oxide exhibits fluffy flakes, etc. and nanospherical structure. Elemental composition shows that it is present in tin and oxide present in approximately 1:3 atomic ratio. Tin oxide undergo, from CV studies we know that tin oxide undergo conversion reaction mechanism. Tin oxide prepared electrodes delivers 1149 milliampere per gram. And the Coulomb efficiency was increased from 61 to 95%. Conclusion, chapter 5 conclusion. Chapter 1 discuss about the micro and nano architecture metal oxide electrolysis and the lithium-ion energy storage characteristics. Chapter 2 discuss about instrumentation used experimental methodologies and characterization techniques, kind cell fabrication assembly. Chapter 3 discuss about NCM composite successfully synthesis to hydrothermal method and inspected lithium-ion transport phenomena, and it exhibits high Coulomb efficiency, long cycle life, huge reversible capacity, good cycling stability, better capacity. Chapter 4 shows the tin oxide nanosphere successfully synthesis via simple and scalable co-precipitation method and inspected the energy storage performance. The produced tin oxide nanosphere provides high discharge capacity, moderate capacity retention, long cycle, and provide considerable energy. Scope of future work. NCM material with a different composition will be synthesized via different methods, as well as it can be composite with nano architectural materials like C3 and 4, MOS2, as well as heteroatom doped materials. The prepared material will be subjected to XRD, SIM, BET-TEM, XPS, FTS spectra studies. The heterogeneous properties of the electrode will be demonstrated in CV brush, the charge discharge and Raman studies. We plan to assemble coin cells as well as pouch cells. Conference and workshops participated in the awards. Senior Research Fellow awarded by Council of Scientific and Industrial Research, Government of India. Best Poster award received from Dr. Parivan, the Research Fellow again in 2019. List of publications. Acknowledgements. I thank my guide, Dr. Sundaravadivel sir, for constant support and encouragement, endless support. I thank Dr. Professor C. Muthyameeswaran sir, Vice Chancellor SMST. I thank Professor S. Ponsan sir, Registrar SMST. I thank Professor K. Kumaraguru sir, COE SRMST. I thank Professor T.V. Gopal sir, Dean CET SRMST. I thank B. Napoleon sir, Dean Research SRMST. I thank John Tirudil sir, Chairperson School of Applied Sciences SRMST. I thank Professor M. Arthanaswan ma'am, HOD Chemistry. I thank Professor M. Sasiran sir. I thank DC members Dr. D. Kalpana ma'am from Sikri and Dr. R. Balay sir from ARCI. I thank Dr. Raghu sir, Managing Director MBM Technologies. I thank Dr. Nyamuk sir for constant support and encouragement. Finally, I thank my family members, seniors, group members, friends and colleagues. Funding agents. I thank CSR for providing last 3 years of fellowship. I thank DST Sarbu for providing lab facilities. I thank SRMST for providing lab infrastructure and the SCA facilities. Thank you.
Now the session for the question.
Yeah, Kumaraguru.
Yes, sir.
First, I appreciate you have done good piece of work, and I liked your thesis, especially the introduction, the way you have written.
Thank you, sir.
Yeah, good one. Okay, so I have some queries and questions generally and technically on this thing. Okay, first thing that your synthesis. So both the compounds you have synthesized in the hydrothermal methods. Okay, and you are using terephthalate also, that one. You are heating to 450, then to 650 also. So is that still some amount of terephthalate acid will be remaining that one? Your IR spectrum, you are showing that no, you have still some amount of organic part attached to that one. So how do you explain that? At 650 degrees Celsius, everything would have decomposed and go.
Yes, sir.
Yeah. So then why do you have them in the IR spectrum? Yeah, anything. Yeah, this is also fine. Yeah.
Yes, sir. In this green color is bad ethylene acid, and the red color is terephthalate acid in oxide composite.
Okay.
And brown color is tin oxide at 450 degrees Celsius. It shows a slight. It is minute bending at the frequencies of 1670 to 1281 corresponds to the incomplete removal, sir. While at 650 degrees Celsius, prepared sample shows flat.
Okay.
So there is some trace in the tin oxide prepared at 450 degrees Celsius. So incomplete removal leads to fading of capacity, sir. Organic matter generally diminishing the capacity of the fabricated coins, so that we go for 650
So
degrees Celsius.
the next question that even if you heat it 650 degrees Celsius, so
Yes,
compound will decompose generally, but there will be some carbon shoots from the system,
Sir,
carbon particles.
yes, sir. We did calcination at the air atmosphere, sir, so that there is no formation of carbon, sir. In case of nitrogen atmosphere, carbon total tetracyclic acid is converted to carbon. We performed calcination at air atmosphere, so there is no carbon trace.
How did you confirm it?
EDS, sir.
EDS.
EDS, no carbon composition was noted.
Are you sure that EDS will show any carbon composition completely?
Sure, sir.
Okay.
And also we do calcination time of 6 hours. And it also play a role, sir. Normally, battery people do calcination of 400 degree, 3 hours, 3 hours and 2 hours, sir. We do calcination 6 hours, sir. So complete removal will be confirmed by EDS also, sir.
Okay. Okay, and you mentioned that you got a spinel phase. What does that means?
Sir, for tin oxide root tail phase, and the NCM was spinel phase, sir.
Is there any reason why you are getting like that one? Is that any your what is the role of your terephthalic acid?
Sir, here terephthalic acid as a act as a template kind of thing, sir. For the preparation of a new, we are trying to prepare a new architecture morphology, sir, by using terephthalic acid, but we end up with the routine morphology nanosphere.
Many people use many long chain compounds for the synthesis, right? So
Yes,
now
sir.
you are using very small molecule terephthalic acid.
Yes, sir. Yes, sir. Actually, we planned to synthesize morph materials, sir, tin-based morph, but we end up in the different direction.
So how do you have the control of the size of the particle, size distribution?
Here, size almost no change in between 450 and 650 degrees Celsius, sir. Almost the same size will be noted, because terephthalic acid is that much big template, sir. If you change the organic mighty bigger or smaller, it will play a role, sir. Only simple terephthalic acid give this kind of morphology also. This was confirmed by SEM also. The two samples also exhibit in nanosphere, sir, with the same size.
What is the size? Average size?
Nearly 20 to 30 nanometers, sir, from TEM.
Okay.
But in SEM it get aggregated, so that not visible. But in TEM we confirmed that it is 20 to 30 nanometer.
Did you calculate the same thing from the Schreier formula from powder X-ray?
Yes, sir. We observed 18.91 nanometers for tin oxide prepared at 650 degrees Celsius. Nearly same.
You are saying 20 nanometer, other one is 80 nanometer. How do you say it's nearly same?
Sir, it was range only, sir, not exactly 20 nanometer. Maybe 20 to 25 nanometer or 30 nanometer. Range only, sir. Not all the particles are not even. Slight variation in the sizes, sir. 22, 23, like that, sir. Majority of the particle in the range, sir.
Okay, but in the other third chapter, what is that? The compounds you showed spherical or cubical particles.
Sir, cubic NCM material, sir. Previous chapter.
Yeah. So that cubes, I don't see much cubes there. Only few cubes are there. Okay, you go back to this one. So there are some cubes, 1 or 2 cubes, but majority of them are not cubes.
Yes, sir. Yes, sir. Yes, sir. Morphology, actually, it get aggregated, sir. So that the difficulty, and 400 degrees for 2 hours sample exhibits almost microcubes. Actually, it is not microcubes, sir. It is not also spherical. It is not microcube. Actually, it is in between.
Some
but
shapeless particles, shapeless aggregation.
and cube is there, sir. But cube's edges are etched, sir. Molded.
So
Etched.
is that anything to do with your terephthalic acid? Probably if you use long chain molecule,
Yes,
you
sir.
would have got some better particle.
Yes, sir. Yes, sir. Better particle as well as morphology, sir. With that also help to get high capacity, sir.
But do you get the what will happen to the conductivity then? If you have so much of organic moieties inside, what will happen to conductivity? Because you are going to fabricate the electrodes here.
Yes, sir. If we have tertiary acid in the prepared material, means it will arrest the conductivity, sir, and also detrimental to the lithium and transportation, sir.
Okay. So how do you select the anode and cathode material for this lithium battery? Based on what property? If you use the anode, graphite anode, lithium cobalt oxide cathode, so how do you choose it?
Actually, the material was constructed. Each material was constructed using material cost and its toxicity to the environment, safety issues while going market. Like that way, researchers designed
That is the main thing to do that. And cost factor comes later.
Yes.
Okay.
Yes,
There is
sir.
some material property based on that we have to choose. Is it based on structure or is it reduction potential or something like that?
Yes, sir. Yes, sir. Yes, sir. Spinal structure is favorable for the lithium.
Your thesis is mainly on this lithium battery. You
Yes,
should
sir.
know that why it is chosen. What is special about lithium cobalt oxide?
Yes, sir. Lithium cobalt oxide has spinel structure, sir. In this spinel, cobalt in 3+ as well as 2+ state, and in the spinel structure, lithium easily go, and while de-insertion of lithium, it will come back easily, sir. Spinel structure favored the lithium and diffusion, sir, in the electrode, so that as well as in case suppose
Do
in case
you know what is meant by electrochemical working range? Working range of the electrode?
Working range of the electrode is for anode is 3 volt up to 3 volt, cathode is nearly 4 volt. And also, sir, instead of cobalt in the lithium cobalt oxide, we place another bigger element. It will occupy the bigger size. It will arrest the lithium ion diffusion in the spinel structure, sir, because of its size. And also cobalt also play a vital role. Nowadays cobalt can be try to replace because of its cost and its abundance, so that researchers are focused to replace lithium cobalt oxide, especially cobalt.
So
because
you are putting your compounds on top of that electrode, or how it is?
Sir, on top of the copper foil, sir. Copper foil is a current collector for the anode materials. With the 9 micron thickness, sir. Copper foil has 9 micron thickness.
Can you just explain me about the fabrication thing?
Yes, sir. Yes, sir. The figure shows the fabricated electrode, sir, and it shows the punched electrode. In this NCM material is 78. Actually, we taken is 160 mg of NCM material. Yes, sir. 160 mg.
You have these cell components, right? One
yes,
picture.
sir. Yes, sir.
Cap, spring, disc, anode,
yes, sir.
gasket. Where is your compound now?
Sir, on anode we coated this anode, sir. This punched electrode used as anode.
Punched electrode is used as anode. So
yes,
that
sir.
means that your compound is replacing the graphite, or graphite also still there?
Try to replace, sir.
No, your fabrication, your cell.
Yes,
okay.
Sir.
So what is that? Is that graphite or graphite coated with your material, or there is no graphite, only your material?
There is no graphite, sir, only material.
Okay. Only your material. Okay.
Yes, sir. Yes, sir. NCM composite.
NCM.
Actually, we take 140 mg of NCM and 40 mg of super P conductive carbon and 20 mg of PVDF, sir, and it is graded for half hour, sir. With the
So your
mechanical
compound structure is known spinel structure, you said, right?
Yes, sir.
How this will also have layer structure like graphite, or graphite? Very important thing is layer
Yes, sir.
structure.
Yes, sir.
That
Graphite
is
has
what
layered
other-
structure.
Hmm.
Compared to graphite in spinel structure, it is difficult to lithium. It is difficult for lithium ion diffusion, sir. Graphite has layered structure. Lithium ions goes easily.
So finally, what do you get? You got better than the graphite, or compared to graphite, you have done all the work now. You have
Yes, sir.
you are trying to replace graphite, and which is cheap and easily available. So finally, what is the advantage you got?
Sir, we got the advantage of 3 times, almost 3 times higher than the capacity, sir.
3 times.
Higher than the graphite, sir. Higher than the graphite result was obtained, sir.
Okay. Did you compare the fabricating the graphite, simply the known method, and replacing, and then compare that your condition, what is the thing? Or you are just comparing literature and saying?
Yes, sir.
I'm asking you,
Yes,
did
sir.
you make the commercial cell in your condition and then using your material and compare it, or just comparison from literature value?
Yes, sir. In future we will do, sir. But commercial things are different from this. In commercial, different separators, sir. In our lab, we use CellGuard 2531, sir. And electrolyte is ECDEC, sir. In commercial, in the lab, ECDMC was used. But compared to ECDEC electrolyte mixer, ECDMC exhibits better electronic conductivity, sir. Better ionic conductivity, sir. So that in the research laboratories normally used ECDMC mixer, sir. Like that, several advantages over commercial materials will be used in the laboratories, sir. Anyways,
Okay.
in future I will do this also, sir.
Okay.
Exactly commercially things I will do, sir, and compare it, sir.
Yeah, I do have another question on the characterization. You have used XPS everywhere to characterize it, right? Show
Yes,
me.
sir.
So these are all peaks are assigned. What is
Yes,
that
sir.
CO2P peak?
Sir, cobalt 2p, sir. 2p electrons, sir.
How do you assign to them the X spectrum?
The binding energy range is corresponds to the 2p region of cobalt, sir.
Do you know how this XPS is done normally? The principle behind this instrument?
Yes, sir. Photoelectric effect, sir. When the photon of high energy, incidents on the electron present in the atom of outermost electron, it get ejected from the electron. The ejected kinetic electron's energy is measured. It is a signature for the each element, each electron, as well as each cell, sir. From this we calculate the binding energy, sir.
Okay. Now another question is that you have been talking about semicircle in your impedance spectrum. So
Yes, sir.
how that semicircle is related to the impedance? What do you get from semicircle? Why it is semicircle?
When frequency high to low, sir, 1 megahertz to 10 millihertz, the interface keep on resistance change of the interface will be identified, sir. It exhibits semicircle.
What
But
is this plus Z and minus Z?
So Z prime is the real, sir. Minus Z double prime is the imaginary part, sir.
What is that imaginary part, real part? Okay, keep reading this kind of things, right? You have been working in electrochemistry for entire thesis, so you should learn all those things. I leave to Dr. Dipankar. Please carry forward.
Yeah, thank you. Actually, you have asked most of my queries. So,
Oh, thank you.
but anyway, just for courtesy, let me ask few questions. So, in XPS spectra, which photon energy you used here?
Sir, X-ray photons.
Yeah, which electron volt? I mean, which photon energy? How much is the photon energy? Okay, let me simplify
Photon,
it.
sir,
You
sir,
use
photon
the aluminum or magnesium K alpha. You have X-ray source, right?
Yes, sir.
So the X-ray source, for example, like in XRD, most of the cases people use copper K alpha
Copper K alpha.
or molybdenum K alpha, something like that. So in XPS also we have typically two sources. Usually people use either aluminum or magnesium.
Aluminum, I think.
So, but you didn't write in thesis. I mean, so which model you use here? I mean, which instrument you use? Let me ask you this. Which instrument is it? I mean, Kratos or SPAX or which one?
Yes, sir. Thermoscientific Multilab 2000 X-ray spectrophoto.
Thermoscientific. Okay, fine. Okay.
Yes, sir. And its photon energy is E equal to h nu, sir.
Sorry.
And photon energy is E equal to h nu. H is the planet.
No, I didn't ask that. I asked about the photon energy. I mean, how much electron volt depending on the magnesium or aluminum. Okay. So now in the XPS, what is the basically typical? I mean, the depth, escape depth of the photoelectron.
2 to 5 nanometers, sir, on the surface only.
Okay, so it's surface sensitive technique, right?
Yes, sir. Yes, sir.
Okay, so I mean that means that you confirm the chemical structure through XRD and then you reconfirm through the different chemical states through XPS, right?
Yes, sir. Yes,
because
sir.
you didn't pass through the entire depth, right? So maybe after 5 nanometer you have a different chemical species, right?
Yes, sir.
So
Yes, sir.
Right?
In case of multi-layer samples, it is difficult, sir. In case of XPS, not applicable. Multi-layer samples, XPS not applicable.
Okay.
Because its
so,
penetration depth is 5 nanometer.
Yeah. So let's say nickel, for example, nickel 2P, you have satellites, right?
Yes, sir.
But then satellites are like very dominating here in the case of nickel 2P. But for cobalt 2P, it is not dominating. It is really looking like satellites. So why in the case of nickel 2P, the satellites are dominating, or what is your analysis?
Sir, actually, nickel present in one oxidation state only, sir, 2+. But cobalt 2P present in 2+, 3+ mixed states, sir, so that the satellite will be low. And also it is in both different environment, cobalt oxide structure as well as manganese cobalt oxide space, sir, so that its intensity, satellite intensity was low, sir.
Okay. Fine. Yeah, this is the broad question that Professor asked actually. So what is the main, I mean, the criteria to selecting the materials, right? So, I mean, in order to choose the, I mean, cathode, anode, or separator, for example, electrolytes, there must be very strong electrochemistry involved, right?
Yes.
So for choosing the materials behind, right? So
yes,
in your case, I mean, what's the main major role? I mean, to choosing the combination of the materials you mentioned, like SNO2 and some cobalt, nickel.
Yes, sir. Yes,
Yeah.
sir. Yes, sir. Yes, sir. In this tin oxide undergo conversion mechanism, it is easily accommodate lithium ion, sir, as well as it has a theoretical capacity of 780, sir. In case of NCM, we reduce the cost as well as actually reported literature contains a lot of cobalt, sir. Cobalt is a highly expensive material, sir. As well as
okay.
so that we adjust the composition of the material to achieve the much better capacity, so that we try this.
Okay, we don't have any cost limitation. Okay, so then how we will choose? I mean, do you think like gold is giving better results here?
Yes, sir.
I mean, you got my point, because that is very important.
Yes, sir.
Question,
yes, sir. Yes, sir.
Then
with by tuning the preparation conditions and preparation methodologies, morphologies, nanospheres, nano boxes, nano porous architectures, core cell structures, by tuning the morphology and preparation methods, with that we achieve better morphology to transport the lithium ion inside the material, sir. With that we achieve maybe better capacity, sir.
But you think more on this question, because this is very fundamental question. Okay.
Yes.
Yeah, and then I mean Z and Z double prime, right? The interfacial resistance, right? You talk about, right?
Yes.
In the impedance
Yes,
spectroscopy.
sir.
So you mentioned about the frequency range, right? Right, but then the low frequency and high frequency, you mentioned something. I mean, okay, can you repeat that?
Yes, sir. Uh, Near origin is a high frequency region, sir. And the inclined,
Yeah, but here you see, here you have a Z double prime and Z prime. Here is no frequency. Maybe it is for fixed frequency.
yes, sir. Yes.
Yeah, because let's say this is F1, one frequency, F and F2, or let's say everything for different materials, but you choose one particular frequency, yeah, because
Yes, sir.
definitely frequency is there, okay, because frequency dependence impedance spectroscopy. But then in this plot, I can't see the frequency variation. Rather, frequency is fixed here. That's my guess. Can you clarify it?
Yes, sir. Frequency is
Yeah.
fixed, sir.
Yeah. So
But-
then how you
but
choose the frequency? I mean here. So you have a wide range of frequency, right?
Yes, sir.
Millihertz to megahertz.
Yes, sir.
Yeah. So how you will choose in the in order to characterize your materials? I mean, which frequency you will choose here?
Actually, normally the
So you have a
electrochemical
different region,
behavior-
right? Dominating region. Let's say low frequency. Maybe you have a diffusion phenomena, right? But in the
Yes, sir.
context of battery, maybe some frequency has a more dominating or more, you have to choose based on your device, right? Or do you think like all frequency has the same, no, not much variation in the context of variation between Z double prime and Z prime? Okay, Z double prime, what is the unit?
Ohms.
Ohm, right? And Z prime is also ohm, right?
Yes, sir.
So what is Z prime then?
Real, sir. Real part of the
Real part of the impedance, right? And Z double prime is the imaginary.
imaginary part.
Yeah. So real part means what is, let's say we have a resistance, capacitance, and another is inductance. Okay.
Yes, sir.
So real part is the, which one is real part among them, among these three?
Resistance.
Resistance. Very good. Excellent. So now you have a other two parameters, right, which governs the impedance part, right? That is capacitance,
Yes.
right? Another is the impedance. I mean the inductance. Let's say we ignoring the induction effect here. So you have a capacitance, right? So
Yes, sir.
this is the plot between the capacitance and resistance in root sense, right? So now you
Yes,
can
sir.
able to think why this circle is coming in some cases much earlier than much or after some resistance, right? If you think between the competition between C and R, then you will have this answer.
Yes, sir.
Okay, fine. So yeah, battery is very important materials. I hope you have a very good postdoctorate positions, right? So
Yes,
did you
sir.
apply somewhere?
Trying, sir.
Okay, this is my last question. So which separator you used here?
Yes, sir. Cellguard 2531, sir. Made up of polymer, polypropylene, polyethylene, sir. Made up of
Polypropylene,
ethylene, sir. Combination of.
So why this is commercially available, right?
Yes, sir. Yes, sir.
So why this is the mostly popular materials that use as a separator?
It is a polymer, sir. It is only permeable to the ions only, as well as it is electronically insulating, sir.
Yeah, there are n number of insulator polymer.
That pore size is for lithium, perfect pore size for lithium and transportation.
Pore size is also tunable with n number of polymers, insulators. So pore size and insulating, this can be done with many polymers. Okay, there must be some other factors involved. Anyway, just another extension of this work for your future work. You can think, how can you also work on the separator? Okay.
Yes, sir.
So if you have lithium-ion batteries, and if you choose a separator for like piezoelectric, for example, I'm working on piezoelectric materials. So if you choose a piezoelectric materials in between, in cathode and anode in between as a separator, then while giving the pressure, you have a liberty to charge up your batteries by means of pressure also. There is a paper in Nano later, because the pressure can stimulate the, the electromechanical energy conversion actually. So you have a potential generation by means of pressure. Then cathode and anode, this recharge. The phenomena may takes place. So you no need any external, port to charge the batteries. You can check that paper maybe in future work. It will be very interesting, because in power, like we have a smart show, for example, we can put our lithium-ion batteries, we can work for a while and then we can charge it up. Right?
Yes. Yes, sir.
Yeah, with this very nice work, because very elaborate work, particularly in the context of COVID, a lot of characterization is needed. You have done also. So I appreciate this, to be honest. And then fundamental is always open question that also we are learning. So you should also learn, right?
Yes, sir.
So I'm congratulating with this, and I'm done.
Thank you, sir.
Kumaraguru, I think you should thank Dr. Mandal. He has taught you about the impedance spectroscopy completely.
About separate.
Yeah. So, any questions from other members?
The session open for the audience, so you may also interact. Any questions? Any clarification you want? Sir, I think no. You may declare, sir.
Yeah, fine. Mainly technical part from the examination board is over. So what next we have to do, Dr. Sundaravadivel?
Just you have to declare the and award the degree, like that you can say. You can award to the doctoral, to the Kumaraguru, and insist to the department and institute to award the degree, like that process.
So I hope Dr. Dipankar Mandal also agree, right? So
Yeah, sure.
Yeah. So on behalf of examination board, I declare that Kumaraguru passed in this voice exam, and I recommend for award of PhD degree to the candidate.
Thank you, sir. Thank you very much, sir. Thank you, sir. Thanks for your.
To Kumaraguru.
Thank you, sir.
So you will be called as a Dr. Kumaraguru. Okay?
Thank you so much, sir.
Yeah. So, and acceptance of the examiner and also the audience. So we can happily call the Mr. Kumaraguru. Hereafter we can call the Dr. Kumaraguru, and also we can appreciate the examiner for the valuable suggestions. And finally, I thank the Department of Chemistry and Professor Napoleon and SRM ISD to giving this opportunity. Thank you very much. Sir, may I conclude, sir? May I finish the meeting?
Yeah.
Thank you very much, sir. I will send the other formalities through the mail, sir.
Okay.
Sir, Mandal, sir, thank you, sir. Thank you. And Muralidharan, sir, very thanks for everyone.
So these formalities, or let's say your documents, official documents,
official
very
document.
quick, I think, right? For push. Yeah.
Yes, sir. Within 2 hours, I will send it, sir.
Yeah,
minutes of the meeting as well as the remuneration form, I will send it by the mail, sir. Just you can put the
See, main thing is the report. If required, report and signature, then that thing you can do a bit fast, because then student will get their official degree.
Yes, sir. Yes, sir. Yes, sir.
And then other thing we can do later also.
Yes, sir. Within 1 hour, I will send it, sir. Already prepared, sir. Just we can send to you, sir. Already we prepared.
Fine. So we'll put our digital signature there, right?
Yes, sir. Yes, sir.
Okay, and then we'll email, right?
Sir? Yes, sir.
So-
Finally,
So
myself and
see,
department, we can put it by manually, sir. Just you can put the
finally.
digital signature.
So first, let's say you ask to Professor Muralidharan first,
Okay,
and
sir.
then I will put. Okay.
Yes, sir. Okay.
Then you take printout, and then you.
Yes, sir. Yes, sir. That is we can
Yeah,
follow.
I'll be going to lab class at 2 o'clock. So I'll be sending you back by 5:30 or 6 o'clock only.
Okay, sir. Just a few minutes, I will send it, sir. If you have the time, you can put it. Otherwise, no problem. We will wait up to 5:30. Tomorrow also we can submit, sir. Within 2 days, we have to submit the official document. That is a rule.
Okay, okay.
Okay, then you have tomorrow time. Okay, fine.
Yes, sir. Yes, sir.
So I thank Dr. Dipankar Mandal also his first interaction with you. For me
Yeah.
also. So nice meeting you.
Yeah, nice meeting you, Professor Muralidharan. Actually, we will also discuss, because I am a chemistry lover, although I am a